second moment of area. We sometimes incorrectly call it as moment of inertia. The second moment of area sometimes incorrectly called as moment of inertia. Actually, moment of inertia is I is equal to mr square, mass time the radius of, or we can say the distance from the point of rotation up to the center of the mass. But here the second moment of area is not the same as moment of inertia. It is actually the second moment of area. So the second moment of area is a geometrical property of a plane cross section. So it is a geometrical property which is based on area as well as its distribution. So what it means, further the material of a section is away from the neutral axis of the section, larger will be the second moment of area. For same cross sectional area, if we make a shape, if we arrange that area in such a way that the material is away from the neutral axis, in that case the moment of inertia or the second moment of area will be high. For example, in these two figures we have same area, but the moment of inertia, second moment of area magnitude is different. Here it is only 6.6 in to power 4 and here it is 166.6. The reason is, in first case the material is close to the neutral axis, and in second case the material is away from the neutral axis. Just by changing the placement of or the distribution of area, we have significantly enhanced or increased the second moment of area. Therefore, the shape of a cross section will significantly affect the value of second moment of area. So if we want to change the second moment of area keeping the cross sectional area of the member same, we can change its shape. For example, for this as well as for this. For these three shapes we have the same cross sectional area, but the second moment area will be different. The stiffness of a beam is proportional to the second moment of area. So this second moment of area actually defines the stiffness of beam. Larger the second moment of area, larger will be the stiffness of the beam. For example, if we see this figure, in the first case the orientation of the member is like this, that the material is away from the neutral axis. So here the I will be high, so the deflection the rigidity of the structure will be more. The deflection will be less and the stiffness of the structure will be more. In the second case, the material is close to the neutral axis. In that case, there will be a excessive deflection in the wooden plank. So here we have a model demonstration to show how the second moment of area is affected by the shapes and it influences the stiffness of the beam. Here we have three plates we have combined in three different ways. Here we have placed it like this, and here we have placed these three plates in vertical direction, and here we have arrangement like I section or W section. So if we apply the load on the first, it will deflect excessively. This is because the moment of area of that section is very less. As a result, the stiffness will be low. In the second case, the moment of area is high and there will be very small deflection. And in third case, the moment of inertia is further increased because of changing the orientation. We have removed the material near to the neutral axis and we have shifted away from the neutral axis. As a result, the moment of inertia will increase. Second moment of area will increase and we will have a higher stiffness of the member. Similarly, we have another model just for the demonstration. If we have a card and if we try to place the book and if we try to lift the book on this card, it will be impossible. It will bend like this. If we hold it over here and try to place a book on this side, so it will bend. It will not be able to lift the book. But if we convert this card in this V shape and then if we try to lift this book on this card, so it is possible. So this is because by changing the shape of this card, we have increased its second moment of area. As a result, the stiffness will increase. So how we can utilize this concept in the structures? So here we can see that in practically we use W section in case of beams. This is just because the W section or the I section have higher moment of area. We have reduced the material close to the neutral axis and we have placed it farther from the neutral axis. As a result, the stiffness has increased. Similarly, if we see these two figures, in that case we have removed the material near to the neutral axis, because the material near to the neutral axis will not contribute much in second moment of area. So we can remove the material near to the neutral axis and the stiffness of the structure will not be affected. So by removing or by punching these holes, it will also reduce the wind loads. So we can get dual benefit. We have reduced the wind effect as well as we have saved the material without affecting any stiffness of the member. Next is how we can calculate the second moment of area. For a simple rectangular section or regular shape, here it is B and this is H. So the moment of inertia is equal to I is equal to BH cube over 12. So this is about its neutral axis, about its centroid. So if we want to calculate the moment of inertia about any other axis, for example at this bottom, then we need to transform this moment of inertia about this axis by using parallel axis theorem. So here this Ix dash, this one, and then we need to transform by adding area times the distance from the neutral axis up to the new axis about which we want to calculate the second moment of area. So we will add a d square to transform this section about the new axis. So for other sections like this T section, so here the neutral axis will lie over here or the centroid will lie over here. So for this rectangular section we can calculate the second moment of area just by BH cube over 12, and then we need to add the second moment of area of these two sections about this centroid. So for that we will calculate the second moment of area of this section, which is BH cube over 12, plus we will add area of that section times the distance from the centroid of this shape up to the centroid, so d square. So in this way, similarly we will also add the same second moment of area and we will transform up to this centroid. So in this way we can calculate the second moment of area of other shapes. For example, we can solve one example over here. We have a T section, or we can say we have a I section. Here the thickness is 2 millimeter and this is 30 millimeter. This is also 30 millimeter and 2 millimeter. The thickness of web is 2 millimeter and the depth is 20 millimeter. So the second moment of area will be equal to about where the centroid will lie over here, because it is a symmetrical section about the both axes. So the second moment of area will be at the center. So the centroid will be at the half of the depth of the section. So I will be equal to for shape 1, for shape 2 and for shape 3. So shape 1 and shape 3 are same and have the equal distance from the centroid. So we can calculate for one figure and then multiply it with the 2. So for figure 1 it is 30 times 2 cube divided by 12 plus 30 times 2 times the distance from here up to the centroid. So this is 10 plus 1, it is 11 square. So we will multiply it with 2 to account for the third figure, then plus for second figure it is 2 multiplied by 20 cube over 12. Here the area is 20 times 2 times the distance between the centroid of this whole figure as well as the centroid of this second figure is same, so it will be 0 square. So from here we can calculate the second moment of area about the centroid of this composite shape. Similarly, we can also calculate the second moment of area for this built up section by using the parallel axis theorem.